Hello, I'm Fernanda Viegas. I'm a principal scientist at Google Research, leading work into human-centered AI. I co-lead the PAIR initiative, which stands for People Plus AI Research. And first things first, this is our team. This is the PAIR team. And today, all the work I'm showing was done by the PAIR team. Let's go back to 2015 when this graph was first made. This is a graph from Wikipedia on the progress in machine classification of images. And each bar shows the error rate of AI systems by year. And the red line is the error rate of a trained human being on a particular task. So the exciting moment is in 2015 when the machines finally beat the humans. And this is a moment of celebration because performance is so high, right? It's also the moment when we start seeing a lot of hype around this technology. In fact, you see all these different headlines on news outlets about, superhuman performance, superhuman AI, superhuman doctors, and so forth. And at the same time that there is so much excitement for what AI can do, that's also when a lot of the big concerns around AI come up, around fairness, bias. It's also when we start hearing a lot of gloom and doom scenarios around AI taking over the world, squashing human creativity, finishing off all jobs, and so forth. And so the public debate ends up becoming very extreme. It's either all the good things and all the hype, or it's all the bad things and all the doom. In a sense, I think what we've got here is a failure to communicate. And so I would like to offer the idea of middle ground, of finding a middle ground. And I think one of the ways we get there is to proactively surface imperfection and limitations in our ML systems. I am talking about AI transparency and explainability. And in fact, when I think about interpretability, explainability, I really think we should have in mind a whole spectrum of stakeholders, not only the AI experts, but a whole set of people who interact or potentially will interact with this technology. What you can see here on the left, I have the most expert users. So these are the software engineers, the ML researchers, the people who are building and tuning these systems. All the way on the right, I have the lay users, citizens, consumers, kids, you name it. These are folks who don't necessarily know about AI, don't understand how ML works, maybe are not even interested in understanding how ML works, but they are on the receiving end of this technology. And I really believe that we owe them a certain level of explainability and transparency. The column in the middle is your domain expert. So these are professionals, physicians, journalists, bankers, lawyers, farmers, folks who have the possibility of interacting with AI systems at a professional level. And in order for them to do that, they will have to trust these systems. Okay, so we're going to start today with the left side of this spectrum. I want to show you some of one example of tool we've created for ML experts. And we're going to start in the beginning. We're going to start with the data. We're going to start with a tool named Facets that we created. It's a data visualization of your data set. And I'm just going to show you a toy example here, CIFAR10, the data set that everybody uses to benchmark image classification systems, or one of the data sets, right? Very simple one. And so now I want to show you a demo. This is Facets, and I'm visualizing CIFAR10 for you. All I'm doing here is I have the images, I can zoom in, and you can see that You can see the images in more detail. I'm putting the images side by side. I'm also organizing the images by the 10 different classes they belong to. Airplane, automobile, bird, frog, you name it. And just by doing that, a couple of things become clear. One is that my data set doesn't seem to have major problems. For instance, it's not like half of my data set is blank or one of my classes is blank, right? The other thing that becomes clear is that there are differences in hues. For instance, airplanes seem to have a lot of blue. That may make sense, right? Because the airplane is flying against the sky, so lots of blue sky and so forth. In fact, one of the things, once I have this richness of information in front of me, I can start to play little games. So one of the games I want to play is to actually reorder this in terms of hue. So now I have all my photos still organized by their label, but now I'm also organizing them by hue. And so lo and behold, both airplanes and ships have the biggest bulges of blue, right? Whereas my animal categories, birds, deer, frogs, and so forth, they have most of my earth tones. So far, so good. It makes sense. Okay, so now let's visualize this in a different way. Let's do a confusion matrix. And the good news is that the diagonal there, in other words, where the humans and my system agree on the classification, that is by far the most highly populated set of cells, right? So that's good news for me. But now I want to go deeper and inspect. So I am going to get rid of all the correct predictions. In other words, I'm going to get rid of that big diagonal there. Boom. Now I'm left with all the mistakes that my system makes. And I can immediately see that there are two cells that are highly populated, these two cells here. And they turn out to be cells where my system is confused between cats and dogs. Who would have guessed? Okay. Now, the last thing I want to show here is another set, another arrangement where I am visualizing the softmax label. And the way you should read this visualization is the more to the right an image is, the more certain my system is that that image is indeed an airplane or a frog or a cat, okay? So good news again is that most of my images are here towards the right, okay? By the same token though, the more to the left an image is in this visualization, the more certain my system is that this is not a cat or a bird or a dog. And just by looking at this, I can immediately see that the most problematic category is cat. By far, it has the biggest number of images here. So we got curious and we're like, oh, what are the cats that my system is very, very sure are not cats? And just by looking into these are indeed, some of them are quite difficult to figure out. By looking at this, we found out that, look at this little guy here. I'm going to click on him. And sure enough, it's a picture that has been labeled by humans as cat, but my system is very, very sure it's a frog. And I have to give it to my system. I agree with it. I also am pretty sure it's a frog, it's not a cat. Why does this matter? It matters because here is a data set that is a benchmark of machine learning. And it's been looked at by thousands of researchers and practitioners. It's been used multiple times, right? And yet it's very clean, and yet it has mistakes. And just by visualizing it, we were able to surface a couple of mistakes right away. So this is a little bit of the power of digging deep, creating tools that allow you to very fluidly dig into your data set and start seeing problems with your data set. What are the limitations of your system here? And so this is called facets. And this is a tool that we use internally at Google, but it's also a tool we've open sourced, and it's being used outside of Google to inspect data sets. Our team has created a whole plethora of tools to help developers, help researchers look inside their systems, try to understand how their systems are working, and as I said, how they might be failing. Please take a look at our website afterwards and check out some of the tools. Now, I want to turn our attention to the column in the middle, the domain experts. And here we're going to be talking about a specific scenario with banks. We're going to pretend we are bankers, okay? So, and this is a high stakes scenario, right? We're going to imagine loan giving. And because it's high stakes, it's even more important to make sure that we are making limitations and trade-offs in the scenarios very clear to our users, to the bankers, okay? So here's how the visualization works. Imagine that each applicant to our bank is going to be represented by a circle. Each circle, each applicant has a score, and each applicant is placed on this graph according to their score. It's all a imaginary credit score rating. It goes from 0 to 100, okay? Now, the color of the applicants is important. Light colored applicants would not pay me back. So these are people who would default on the loan. Dark colored applicants would pay me back, and these are the people I want to give loans to, okay? Okay, so I have multiple people coming to my bank. I set a threshold here. In this case, it's around 50. Anyone below 50 whose credit score is below 50, I do not give a loan. Anyone above a credit score of 50, I give a loan. Wonderful. This would all be simple and great if life were this easy, but it's never this easy, right? Reality is much messier than that. And it turns out that chances are, no matter where I put my threshold, there's always someone I'm going to give a loan to who does not pay me back. And there's always someone I decline a loan to who would pay me back. In fact, this is still very simple, but this gets closer to a true distribution in a population, okay? And you can see how I can play with the threshold, but it's never really perfect. In fact, there are more indicators I care about. So not only do I care about my loan threshold and how many people I'm, denying loans to or giving loans to, I also care about this indicator on the rightmost hand side here, positive rate. So what this means is, of all the people who come to my bank and apply to a loan, what is the percentage of people who are getting loans from my bank, okay? And then there is the true positive rate. This is, of all the people who would actually pay me back my loan, what is the percentage of those people whom I'm giving loans to? Okay, so multiple indicators there we care about. Now, if this weren't hard enough, I have yet a more interesting scenario, which is, imagine you have multiple populations of applicants coming to your bank, asking you for loans. And these different populations have different distributions, and I know that. Okay, so the blue guys and the orange guys, they look different in these distributions. How can I, as a bank, be fair? And this is where we're going to go to our demo. So this, again, is the same visualization I was showing you before. I have my blue population, I have my orange population, I have thresholds. I can play with these thresholds here on the blue population, on the orange population, and it's all good. But I also have a certain set of presets here on the left-hand side. So in fact, if I'm a bank who doesn't care at all about fairness, I may just want to maximize my profit. I click on this maximum profit. It highlights this for me. I can see that my threshold is different between these two populations, and all I care about is money. Okay, what if I am indeed trying to be fair? What would be the best way to treat my applicants? Maybe one way I could treat them is to say, you know what? I don't care if you're blue, if you're orange, I'm going to treat you just the same. A metric called group unaware. I am going to set the same threshold to all of you because that is the most fair thing to do. Okay, once I do that though, I have the same threshold, everybody's treated the same, but look at these positive rates here at the very bottom. Whereas I'm giving loans to 52% of all the blue people who come to my bank, I'm giving loans only to 30% of all the orange people who come to my bank. Is that the best way to be fair? Maybe, maybe not. Well, let's think about a different kind of way to be fair, a different kind of metric called demographic parity. When I click on demographic parity, what I'm optimizing for is exactly this positive rate, right? So now I am giving exactly the same percentage of loans to the blue people and to the orange people, 37%. That's fine. My thresholds are different for the two populations. But look, in terms of true positive rate, the percentages are still very different between the two different populations. I am giving loans to only 64% of the blue people who would actually pay me back, whereas I'm giving 71% of loans to the orange people who would pay me back. So we have yet a different way of thinking about fairness. We have something called equal opportunity, which optimizes for the true positive rates. Okay, I could go on and on about fairness, mathematical fairness metrics here, right? Because the truth is there are hundreds of them. You can keep tuning these things forever. But the main point I want to make here is that by surfacing these different choices and by making very clear that no matter what choice you make, you are setting up a number of trade-offs. This is what we want to highlight here, okay? And in fact, by highlighting this, by making this clear with a simple visualization and a simple simulation, we were able to broaden the conversation online, the public debate. In fact, we had discussions, we saw people discussing on Twitter about say, oh, I always thought, demographic parity was the way to go. Now I see that equal opportunity could be more fair, if you will. Other folks were reusing the visualization technique to think even deeper about things like long-term use of fairness metrics and whether or not those were desirable. Another thing that happened was that once we put this online, we started getting emails. So emails, for instance, from criminal justice departments. I remember getting this one email where a criminal justice department in the US said, do you think we could build a visualization or a tool like this for our department here so that we could better understand the trade-offs we are making in the criminal justice system as we're using different algorithms? Obviously, we're not giving out loans to people, but we're also using algorithms. And it would be incredibly empowering for our staff to better understand. So after we saw the kind of impact and the kind of conversation that came out of having this toy example, we decided to go from toy to actual tool. And we created something called the What If tool, which, again, we use internally at Google, but we have also open sourced, and then lets you probe these machine learning systems code-free. You don't have to code to be able to ask questions about different thresholds or different fairness metrics. In fact, we already have, the What If tool already has a number of preset mathematical fairness metrics that you can play with to try to understand for your system, for your data, what would be some of the different scenarios in terms of thresholds that you might want to explore. Again, with all the different impacts, right, for your population and for your context, okay? The What If tool is also available on Google Cloud AI, and the whole point is to make sure that whatever enterprises use this kind of technology do so responsibly, that they understand when they're playing with these different thresholds that there is real impact on in the real world in terms of who gains and who doesn't gain with these decisions. And again, making these decisions very easy to see is a very empowering move. Okay, I'm still going to stick with the domain expert column for one more example. And here we're going to talk about physicians. I'm going to just take one step back to remind you of TCAV, which is a high-level interpretation method created by Bing Kim and others in our team. And it stands for Testing with Concept Activation Vectors. Why am I talking about this? Very briefly, because this is one example of interpretability method that meets the user at a human level, not at a machine level. If I ask the system, for an image classification system, why do you think this photo is a photo of a zebra? Instead of the system giving me, oh, because this pixel here and this other pixel are important, I want the system to speak my language and to tell me things like, was the concept of stripes important in your classification of this image? And to do that, what you want to do is understand that if, for TCAV, if you have enough activations of striped images, not zebra images, images of any images of stripes, you can represent how they are different from other images as a CAV, as a concept activation vector. In other words, we'll find for you the direction that captures the concept of stripes, okay? And if you move more in that direction, that you're going to be moving towards the concept of stripe. If you move away from that direction, you're going to be moving away from that concept. Why does that matter? It matters because by creating this technique, we have translated from an easy to define human-friendly concept, stripes, into neural network geometry. And by doing so, we have all of a sudden allowed end users to potentially speak to machine learning systems. What does that mean? Well, we'll see next with doctors. We're going to turn an interpretability method, TCAV, into a tool where doctors will call the shots, okay? So here's our scenario. We're working with pathologists trying to diagnose cancer. And so what pathologists do, they will look at a big image like the one I'm showing you here, which is a tissue from a biopsy from a patient, and they will try very hard to understand, is there cancer there? And if there is, what granularity of cancer is it? What level? Is it Gleason 1, Gleason 2, Gleason 3? And it turns out that this is hard to do. One of the things they try to do is to compare the image they have of the patient in front of them to other cases they've seen before and cases they've diagnosed before, okay? So you may be thinking, well, that's a simple image search problem, right? I just give the computer the image of the current patient and show me the nearest neighbors. Yes, you could do that, but it turns out there's more things that are important. They're very important when a doctor is trying to diagnose something like this. It turns out that doctors have multiple dimensions they're thinking about. And a lot of these dimensions, some of them are very visual, but some of them are medical concepts, like level of stroma, normal glands, the percentage of tubular glands, the percentage of fused glands, and so on and so forth. And a doctor is usually looking at this image and thinking, I wish I could get images with more fused glands. Show me the nearest neighbors for this image, but with more fused glands. How do we get a doctor to express to a machine that concept of the query they want to do? So this is what we did. You take a concept like fused glands, which is a human concept, and you turn that into a CAV. You find the fused gland direction, okay, in the neural network. You give it examples. So we asked the doctor to populate a CAV with examples of fused glands. And then we found that direction. Once we had this CAV, we turned it back into an actionable user interface element. So all of a sudden you had a slider where you could go from more tubular glands to more fused glands. And that gave doctors a very powerful way, kind of a very powerful flashlight to look into this highly dimensional space. What we ended up doing was creating Smiley, a search engine for doctors that not only brings to doctors the nearest neighbors to the current patient they're looking at, it also allows doctors to query the system with very powerful medical concepts, like the concepts I was talking about before. And by doing this, we ran a user study with 12 pathologists and found out that all 12 pathologists preferred these tools over an traditional ML-only interface. What do I mean by a traditional ML-only interface? This is when you give users either just a number, a probability, or just the nearest neighbors with no way of digging deeper and asking more expressive questions. So this was work done by PeyKy in our team with others. And to me, it shows very much the power that we give users once we turn these interpretability tools back into actionable tools. Finally, I want to end by talking about lay users. We're going to talk about a consumer product here. About a year ago, we published the PEAR Guidebook. And this is a guidebook that distills research insights and our industry experience at Google into concrete guidelines. You know, when everybody talks about, oh, we should build fair machine learning, or we should build unbiased machine learning systems. And everybody's like, yes, great. But how do you get from those lofty principles into concrete steps? How do you do that? So the guidebook was our first attempt at starting to answer some of those concrete questions and give some concrete guidelines. So here's what I want to talk about. One of the chapters of the guidebook is about explainability and trust. And the scenario is a running app. Imagine you have a running app that's going to give you suggestions for running routes. And you have injured yourself, and you want to ask for a recovery running route. Okay, so this is kind of a high stakes scenario because you were injured, you have to be careful, you want to make sure you can trust the system. And so the system may say, okay, recovery route details. We have adjusted your normal route to aid in your recovery. Great, but how? How are you doing this? You're not explaining to me. Do I trust you? Should I not trust you? So let's not do that. Let's do something better. Let's give details of how we've made this adjustment. So the recovery route details here for your new route include minimal elevation, an even surface, and we're setting a slow pace. So you can decide if you want to trust the system or not, because now you have a higher level of transparency. A different scenario, you want to go for an evening run. You ask for an evening for a route recommendation. The system says, night moves. Be careful on your evening run. Oh, be careful. Why? What do you, system, know that I don't? So instead of being mysterious like this, let's be clear. Let's say something like, be careful. It's after 6 p.m. and our run route recommendations don't include street light data. So here again, I am going back to the data I have. I am surfacing to the user my limitation. I don't have street light data. And I'm now empowering the user to decide for themselves. Do you want to do this route? Do you not want to do this route? And this is an incredible step to be able to go from limitation to possibility. Okay? And so hopefully I've impressed upon you the importance of thinking about explainability as a wide range of stakeholders. And also by surfacing these limitations and these imperfections in our systems, I really believe that this is the only way we're going to gain trust and gain more traction and end some of this very extreme debate around AI. Let's be clear, let's be honest, let's be transparent about the systems we build. Let's talk about their wonderful qualities, but let's also talk about their limitations. Thank you so much.
Hi, everyone. Thank you so much for joining the live Q&A session today. So with us, we have Fernanda Villegas. Thank you so much for joining, and thank you for the incredible talk. It was so good. For those of you who have questions for this speaker, we have two ways to ask those questions. So one is to just copy and paste your question into the Rocket chat in the website that we have, or you can also type your questions into the Q&A chat box on the Zoom. And yeah, why don't we get started? Okay, great. We have one question. They said, thank you for the nice talk. How do you define the patterns used in TCAV?
Okay, so first, thank you for having me. So the patterns in TCAV, it's a good question, and there's a whole paper you can look up afterwards, but very quickly here, imagine you want to grasp the notion, as I think I said in the talk, of stripes, right? To understand if stripes is important for the image classification of zebras. What you do is you seed a bunch of images of stripes to TCAV, and basically these can be stripes of anything. I'm not talking about stripes in zebra. It can be like fabric stripes, crosswalks, anything that has stripes. And you feed those examples to the model, and what you do is the model then captures that vector, that direction. So you have on one side all the images that have stripes that you fed it as examples. And then on the other side, you have random images of anything else. And so TCAV will find for you that direction, and that becomes the concept. This is the way that you capture that concept, if you will, in TCAV.
Great, thank you for the response. We have another question from the audience. Do you think that some of the tools could be used to reveal biases in the data itself? Some of the tools that you discussed?
Absolutely. So just because, for instance, we were talking about TCAV, for instance, one of the uses of TCAV is exactly in trying to uncover biases. So what do I mean by that? Imagine you have, again, an image classification of a doctor. And you can ask what concepts were important for this classification as a doctor, professional. And maybe some of the concepts that the model has found very important are things like a lab coat or a stethoscope. And those are all very good concepts for the decision that this is a doctor. However, if you also find that concepts around gender were important for this classification as a doctor, that may be problematic. So you may want to check on that. So that's one way in which you can use something like TCAV to uncover bias. Other techniques, the more visual techniques, in fact, that uncovering bias is one of the other reasons why you want to have these tools. So not only as explainability tools, but also as tools that will start to let you see some of the imbalances you may have in your either your training data set or how your model is behaving.
I see. Along those lines, for both the demos that you showed, like in the facets example and also the what if tool that you showed in your talk, how do you typically go about deciding which features or visual characteristics you should prioritize for the end users?
For end users, the what if tool. So let me take a step back. It depends on who your end user is. If your end user in this case, for instance, using the what if tool, is a data scientist. Some of the things we do, for instance, on the what if tool, one of the things we try to do automatically is we try to surface for you the list of features that we think are, for instance, the most unbalanced features. So either there is a weird distribution, or maybe these are features where half of the values are missing or something strange. And so we automatically try to surface that for you. But the truth is also, a lot of times we're not going to be able to automatically find the problem. So this is part of the reason why you want tools like the what if tool. So you, the human, can go in and inspect and try to understand, okay, what may be the features that are problematic here. One example of how you might want to do that on something like the what if tool, it has what we call counterfactuals. Now, I say that in quotation marks because this is not a causal notion of counterfactual. This is more like, imagine you are a bank, you're trying to decide on a loan, and you've given, you find someone in your data set who did not get approved for a loan. What you can do then is say, okay, anchor, what if tool, anchor on this person, and now show me the closest person to this person I denied a loan to. Show me the closest person who did get a loan, and highlight for me the deltas between these two people, the person who didn't get a loan and the person who got a loan. And that's how you can start to understand. And then it's up to you as the human to decide, okay, maybe some of these features are okay, and yes, I can see how this person got a loan and this person didn't, but maybe some of the features are not okay. And so that's, again, how you start to dig in and understand, is my model doing the right thing, or do I need to tweak it? Do I need to improve it to make sure it's behaving responsibly?
I see. It seems like it requires a lot of thought in sort of really deciding like what features the model should focus on. And yeah, on that note, what do you think are some of the major challenges for these tools going forward, especially as we start incorporating these methods into models into that go into production and are used by like millions of people downstream?
Yeah, I think some of the challenges are things like, what are all the signals we can try to get automatically from these models versus what are the things where human